And for anyone who wants to follow along the tutorials, I recommend to go on the Indico page, and there you see the material that is provided. Click on the link of all talks and run in Binder. Binder will open a window in Binder, and you can just directly go from there and run it. All right, so this is also split, as mentioned. There's my talk, and there's going to be the talk from Jason afterwards. Jason will talk about the latest news in zfit, so the latest development. If you're already a user, then that's interesting to see. But I will introduce you to how we do fits and statistical inference in Python. So first, that we're on the same page. Little quick start. What is zfit? What is model fitting? What I mean by that? We'll just go through. You can meanwhile load the binders and open up the other tutorials where we will go more into depth of things. So we have first imports, zfit, mplhep, matplotlib. It's a fitting library and it's well integrated in the whole Scikit-HEP ecosystem, works well with all the other libraries, as we'll see throughout. How we do fitting in zfit is we first create an observable. That is a zfit.spice, a bit like roofit if you're familiar with it. This just defines the axis of our data. This is now an unbinned example. We'll also go to binned examples. Now, some warnings, don't worry, that's just TensorFlow saying some stuff, but ignore these things. If you load, we can create some data, just sampling from NumPy and loading it here. So we have a data object, and now we can create a PDF. We create some parameters, name, value, lower upper bounds. We can say a step size, doesn't matter. It's similar to something like roofit. It's just some basic fitting stuff. We can create a Gaussian, and we can quickly plot this Gaussian. That's what it looks like. We can do things with that Gaussian. It has PDF and so on. But for now, we just go for fitting. If we want to fit this Gaussian to the data, so we have now our model that is Gauss, and we have a data object. We can create an unbinned negative of likelihood. Likelihood fits, sure you've all heard of them. We can create a minimizer like minuit using iminute behind the scenes and minimize it. So let's quickly do that, and we'll get our result. So I assume every one of you has, in one way or another, already fit something. This would be fitting a Gaussian to some data. Now, plotting the PDF is done here. That's our result. And we get some information on the result. We'll go more into these things. I'm going a bit quickly through it just to give you an idea of what this is about. And we can also calculate some uncertainties, hesse, or minus errors. I'm sure you all are familiar with those as well, or have heard of them in one way or the other. We get the result. And in the end, we can also store a result. Again, we'll go more into that, but we can dump it. We can load it again. We can plot it again. And we can even dump it in a way that we see the whole model and can actually publish it. Now, in the following tutorials, we'll go through all of these steps again. We will create more complicated models, more complicated likelihoods, do more complicated plots, load different data, and play around with all these elements. But in general, this is basically what zfit does. So the rest of the tutorial will cover these things. And by the way, if you have questions, yeah, something on the tutorial, then feel free also to ask if we're at a certain step. All right, what we've seen before is doing a fit, creating a model, creating some data, using the space to define the axis, creating a loss, that's a negative for likelihood, minimize it, and get the result. So let's go through all of these elements in a bit more detail, because this will help you to set up actually a bit of a more realistic fit. Once we've established all of these elements, we will also go together through a more complete example of what we can actually do. So data. I mentioned data. but data is not so important in a fitting library. So it is in zfit, but the main purpose is just to have a uniform format. It's highly compatible. You can create data from pandas or NumPy. You can do it uproot. You can give in a hist from the hist library or anything similar. This is fully compatible, and some objects even usually you can even just give NumPy data directly. That's not a big deal. So all of the pre-processing is kind of left to other libraries. Now we extend our fit a bit, but as before, we need to define what is the axis that we have our data on that we actually want to fit. This is a bit like a column in a pandas data frame. We can also provide a label, which gives us something human readable. The space object defines a few things. It defines, for example, the limits, the lower and the upper limit of our space that we're in. It can give us the volume that we're in, because it can also be multidimensional. Labels, as I mentioned, give us something of like whether an event lies inside or not. And as we'll see later on, it can also provide some binning. A bit like the real war, if you're familiar with zfit. Now we can, again, do the same thing, create some data, and we can load it. There are basically two ways to load data in zfit. One is using directly the data object and give in whatever you want, NumPy array, pandas, hist, and the thing usually work. Or with an explicit loader that is zfit.data, and then you can say from NumPy, from uproot, from hist, from whatever you want, and that has a bit more options. So both methods are perfectly well valid. This data object that we have has a few things. It tells us how many events we have in there. It has a space that is just the axis we defined before. And we can also just get a subset of the data. So it's a bit like a pandas data frame. We can also index it a bit like a pandas data frame. So we can print some information. And we see the first thing that we have now 9,000 events, although here we sampled 10,000. And the reason is because the space that we defined goes from -5 to 10. But we have a Gaussian with 2, that means a few events are outside. So that's the only pre-processing that zfit applies, is it cuts the data to within the space. And we know the number of observables is 1. We just have one axis, just like number of columns. Now, building the model is probably the core part of zfit. A model is in general a PDF, and that is normalized to 1. But we can also have extended models, we can have bin models, and so on. I'll leave this text and continue. That's a bit the start of the tutorial, by the way. I'll go a bit over what is where so that later on you can come back and remind yourself of the things that actually are relevant. But building a model means we have a PDF, like a Gaussian, like something more complicated that we actually fit your data. And for anyone more CMS Atlas, it also means stacking some histograms, adding some nuisance parameters there, and so on. It all goes up into the same thing. So one crucial thing to build our model that we want to fit the data is the concept of a parameter. This is a thing that in the end we're interested in, and the parameter has a name that is a unique identifier. It has an initial value, a lower and upper, and we can give it a step size, say if it's floating or not, and also give it a label or something like that. And these are used to parameterize our model. Now we can just create these parameters, and we can also just change these attributes, say it's floating, true, or false. That's all there is. And now with that, we can create our Gaussian model by giving in these parameters. That means this Gaussian model now depends on these two parameters. And similar to data, this Gaussian model has some attributes. It tells us the number of observables, so the number of dimensions. It gives us which observables. It also has, like the data, a space, which tells us from where to where, what are the limits, and so on. And the normalization range, which usually is the same, and by default is the same as what is defined over. That's also a bit more advanced use, but that you have these attributes there. It also has something called params, which maps the parameterization to the actual parameter. These are two different kind of names. I mean, the Gaussian is always a mu and a sigma, and the mu here is mapped to the parameter that is also called mu, but the sigma is up to the parameter that is called sigma 42. We can also retrieve, and that's the best way if you want to retrieve what all the three parameters that my model depends on. I mean, in a Gauss, it's probably trivial, but more generally, if you have sums of others and stack histograms and all these things, you want to know, okay, what parameters are we actually depending on also indirectly? And that's where you can use the getParams function, which has a few nice options. For example, you can say, do you want to have some that are floating or not? Do you want to have them if they're a yield or not? So if they scale the whole PDF to the expected number of events, and whether it should follow all of the things. So by default, it really gives you just what are, in the end, the free floating parameters, which is very useful for a fit. Now, yeah, if we would, just to give you an idea, the difference between the two methods, params really says like, okay, what is mu, what is sigma here? And getparams gives you all of them unordered, doesn't need to depend on Gauss directly. An example is if we would create a Gaussian and use mu for both the mu and sigma, we can do that. And then if we say, give us the params, it gives us, okay, mu is this mu and sigma is also this mu. However, if we call getparams, obviously it just returns us one single parameter. So that's the difference there. Now, PDF has, of course, functionalities. It's basically distribution, and it has the PDF, integrate, and sample methods. These are the most important ones. The binned will have two more, but for now, let's look at these. Integrate integrates the PDF and gives back a number. Now, as you may have noticed already, there's the thing of TF tensor and NumPy and what the heck is that? And don't be scared. There is just a way of if you're implementing something on your own, but for it, just think it's basically NumPy. So if you, for example, call a NumPy function on integral, it just creates a NumPy array. So don't care that this returns a TF tensor. And if you really want to have an array, you can always call np.asArray on this object, but usually it's not needed. You just continue calculating as if nothing happens. We can sample as well. This draws randomly some samples, and sample is again a data object, and the data object cannot just load from pandas. It can also just be converted back to pandas. So if you want to get something nice, you can use NumPy for sampling, but you can also just use zfit for sampling if you have something more complicated that is not available in NumPy, for example. And you get your pandas data frame and play around with that data. You can also just give, instead of making two pandas, you can also hold that value, which gives something array-like. You know, this is NumPy-like, this tensor thing, but doesn't matter. It's like NumPy. And then you can do NumPy.absolute on columns as well. You can get, like in a pandas data frame, the column out of this data object. So if you sample, it's very useful to do things. You can also convert it directly to NumPy. And it also has a bit of information, again, as a data object before. So you see the data object is very much interchangeable and goes back and forth to all the objects in Python that we need to know. If you're interested in bin fits, yeah, that goes to the same stuff. We'll see that later on. All right. Gauss PDF just evaluates the PDF at these points, and we get the probabilities back here. I just want to note here that we're not going into toy studies, but toy studies, there's just a more efficient way of doing this whole fit that is described on the page. We're not going into details here, but it's basically the same stuff. Now for plotting, we can use matplotlib. Straightforward. It's just a bit of boilerplate code. We evaluate the PDF, we scale it correctly to fit the background data, and so on and so forth. And that looks like this. There is also a shortcut, which is we can just use a plotting interface from the PDF itself. That is a bit experimental still, and maybe changes a bit, but it gives us a quick access to just plot the PDF. Makes life easier for everyone. Now I've shown a Gaussian, but zfit has a lot more models. This is just an overview from binned and unbinned and KDEs and whatever not. And we also have zfit physics. That is a package which contains many physics-specific relativistic Breit-Wigner or Novosibirsk PDFs that you may want to use. So to create something more realistic, we can also have a crystal ball function, for example. We can create a combinatorial, and we're just plotting it just to show it. We can create a combinatorial, vector, and exponential, and have a KDE for some template of our background. Again, we can just plot it here to visualize this. So we can assume that we want to have a mixture of the three components in our data. And for that, we can just use the sum PDF. We create a fraction. What is its value? We have three PDFs. So if you have two fractions, that is like the loss is 1 minus the sum of the other two, and we can just easily plot it. You see this as well. Plot components just plots the components individually, so without stacking or anything fancy. And we get a nice view of what it is. So we can use fancy stuff as well with parameters. We can set them just temporarily so that inside here, the parameter has a different value, and that can be useful, for example, if you want to sample from it. So we just say, okay, inside this width, set all these values to these values, these parameters to these values. Now, that is one way to do it. If you want to do something longer that is maybe convenient, you can, by the way, also give a dictionary, but you can also do it differently. You can simply say, well, sample from the PDF and take the parameters to have these values for the sampling process. This is a more modern thing. You can basically, whenever this is needed, you can just give in params, even just as their string names, to say which values you want. And then we can plot it again. This is the model, and this is the data. They look different because we sampled from a different model. We can also plot things manually here. This is just another way of plotting it, and then we have the same thing. Now, one thing that I didn't mention so far is the extended PDFs. I said the PDFs are normalized to 1, but sometimes it can be good to have a parameter which changes the number of events in our bin, so to speak. If you're more CMS and Atlas, then I think you're doing always basically extended fits, and it's always a matter of where do these histograms go through the signal strengths, or mu, often also called. And we can do that too. We can just create a parameter that we now call the yield. This is meant to be the expected number of events that we see. And we can create an extended model, either from taking a model that we have and then say create an extended. Or what we can also do is we can, whenever we create a model, like a PDF, we can just say make this extended directly. So there are two equivalent ways of doing that. What is even more common, obviously, is to create the components already extended. So say, okay, I have one component that is my componental background. I want to know how I give that a yield. I have my signal that has going to be a certain yield, and so on. This is how you would create it. You see, Gauss takes this extended combinatorial. We just do from create extended, and this one we create with extended, just to show the two variants. And now we have all three components as extended PDFs. And that means if we now create a sum, we don't need to specify the fractions. We can still, and you still have full control, but you don't need to. And then it creates all the stuff behind the scenes automatically, and also makes this model extended sum automatically extended. All right, so we have now a model, some mixture of three components. Each of them has their own yield, so it knows how many events to expect, and that is summed up in the sum PDF that we have. That's our model exercise. Now we can fit things. And to fit things, we want to have a unbinned negative log likelihood. Now, if we just take the unbinned negative log likelihood, it won't take the yields into account. It will just fit the shape. Sometimes we're not interested in the yields, for example, if you're fitting to simulation, but sometimes we are if you're fitting to data. It will warn if you're fitting something that is extended and you're fitting it with an unextended loss. It's just two different types of loss. So we have our negative log likelihood just using our Gaussian here, not the complicated model for the moment being, and we can just evaluate that. So this gives us the loss at this point. This is the negative log likelihood value. And yes, you can do things more complicated with it, as we'll see later on as well. This loss has also a model attribute, which tells us what are the models associated with it, and data attribute, which gives us what's the data object that we're having. And same as models, we can say get params, so give us all the independent params. This is a thing from our Gauss. If you want to do an extended one with our actual model, we can do that. It means we're getting a few more parameters here, but that's all fine. Now we want to minimize this NLL. Minimizing the negative log likelihood is the same as maximizing the likelihood to find the optimal parameters, which we can do with minimit. I'm sure you've probably heard that. It uses iminit, but there is also, I don't know, 20 other minimizers available in zfit, from nlopt minimizers to scipy minimizers to ipyopt, and they've been strongly equalized in terms of names. So you have all this time the same convergence criteria, you have all the same names for tolerance and so on. So if you minimize with another thing, another minimizer, it will give you the same and an equivalent result. But minimit is usually the best, especially for unbinned fits. Others take a lot of time to calculate this criteria. So we create a minimizer, and that's fine. And then we can just call minimize init, which basically takes a loss, and we can also say some other stuff. We could pre-fit some parts, for example. This is just an example of how can we fit just parts of the PDF. We can create a truncated PDF, but that's not so relevant. Just saying we don't need to always fit all of the parameters here. We just fit lambda. If you're interested in a piece of code, have a look at it later, and then just fix lambda here. But we can just fit our whole PDF, and then we can also plot it, and this is what a fit looks like. We can have a look at the fit result, and the fit result tells us what did we actually fit, what are the models and the data, what is the minimizer that we've used, is it valid, did it converge, are the parameters limit, just a bit approximation, what's the estimated distance to minimum, and what is the value at the minimum. This is some optimized value, which usually you don't need. And these are the values. Now, we can also just print the params itself. You don't need to always have the full result, and access them here if you want to get anything out. So, for example, like this, we get all the information that we have about musing. And we can also get the fmin and some other things. If you want to now estimate some uncertainties, we can use, for example, hesse. Minute hesse, for example, or we also have a numpy implementation. And now the result changed, and we have this hesse information here as well. We can similarly also call minus, and then we get this huge information back that minus gives us. But more simply, we have the print result, and errors are here. These are asymmetric errors that use some kind of likelihood profiling. We can do this also manually. If you want to do a likelihood profile, this is an example. We just evaluate. We say that signal yield, for example, is not floating. Then we iterate through all the values that we want to test the signal yield for. We set it to that specific value, minimize again, and then append the actual likelihood value. This is basically we're marginalizing. And then we can plot it. And also get other things out, like the covariance matrix or whatever we are interested in. There we go. This is the likelihood profile. The minimum is a bit more to the left. So we should do another scan more to the left. We'll look at the covariance matrix and many other things. And last but not least, we can also just save and load our results. We can use dill to dump it. zfit.dill is just a drop-in replacement for dill. It just has a few things that make sure that the garbage collection and everything works. And we just dump our whole result. That is usually enough to dump the result, because the result has a reference to the loss, and that knows the model, and that knows the data, so everything is in there. But you can dump anything. You can dump any Python object. You can, for example, like here, just create a dictionary that contains a list of other things and covariance and whatever. This dill is like pickle. It just dumps your whole Python object, and you can later on load that again. One thing is just dump your whole model at once and load it at once. Otherwise, it's a bit tricky with the parameters that the names are matched and so on. There's another way as well to dump, and that is still a bit experimental. It's a HF3-like format, not exactly, but it's close to it. And that means it dumps it to a human-readable format. Now, if we can dump the loss, and this gives us a lot of things, but basically it's a format that you can like read, and it tells us, okay, what kind of PDF is it? It's a Gaussian. Oh, it's extended by the signal yield. Signal yield is a parameter. The parameter is that. This is it. This is a sum, actually. There's also an exponential and a KD, and so on and so forth. Now, that looks a bit complicated, but it really is a way of conversion that we can publish actually likelihoods in HEP. You can also just dump, for example, the signal PDF to a YAML file. And then here we have a YAML file that describes the signal PDF. This can be loaded again with zfit. It's a little bit experimental, but most of all, you can also exchange it. You can just change the numbers and load that back in if you want. Now, what we have not done so far is some more statistical tests like limits or anything like that. And for that, we can use hepstats. Hepstats is another library in the Scikit-HEP ecosystem, but it's built around the zfit. Well, it's built around an API, and zfit also uses this kind of same API to calculate some more sophisticated stuff. And that means, for example, if you want to have some confidence interval, we just say, okay, we want to have this confidence interval and we want to calculate asymptotically. We can calculate things in different ways, but one way is asymptotically. So we kind of just take the log likelihood and assume this is like well behaved for a large number, for n going to infinity. This all works. But we also have something called a toy calculator, in which it just throws all the toys. So it kind of fits different it draws different samples and fits them back and sees where all the values go, which is a lot more expensive, but also precise, especially if you have not so many events, then this should be used. Now, we can just say we want to scan this region a bit like before, but now we do it a bit more sophisticated, and we say, okay, this is the parameter of interest array that we want to scan. We want to get a confidence interval, so with the calculator and asymptotic calculator, that goes from this result, and with this minimizer, and we say this is the POI array to scan about, we call it, and then this will calculate as intervals. And then we can just plot this. There's a little utility in the repo, and we get our confidence intervals. This is the basics of zfit. These are all the elements, how they're meant to be used. Now, we can go to the next notebook, and that is called binned fits. What we've done so far has been for unbinned fits, but binned fits work in a basically equivalent way. You can also mix them, you can put them together, and this just introduces what is basically the difference to binned stuff. So for anyone CMS Atlas that is probably becoming more interested, or anyone who's using large amounts of data and wants to do analytic shapes. So as said, instead of some PDF is binned some PDF, instead of data is called binned data, instead of unbinned NL, it's binned NL. That's basically the difference. The good thing is also that it integrates even a bit better the ecosystem, but let's go from an unbinned fit to a binned first. So we can create again our Gaussian fit from before. You've seen that stuff multiple times. This is how you do a fit in zfit. So Gaussian sampling parameter, we create a minimizer, and yeah, we could minimize that. But now we want to do this whole thing actually binned. The easy thing is we can just build this stuff until here, and now we want to do binned in the last step. And there are a few ways to do it, but if you're already having things unbinned in zfit, we can just say, well, data to binned with some number of bins. This will create a new data object that is now binned. This data object also has a space, and this space will now be a binned space. So we can just say, okay, bin the same model with the space from the data, because that is now space. This is now binned space, and so we have a binned model. And if you want to create a loss, we need a binned negative log likelihood now. Now, from here, the game continues as before, and we minimize it. Bam, and we get the Hessian uncertainty, and we get the minus uncertainties, and we can again print the whole result. So no difference. That's a bit of philosophy. Yeah, you need to change a few things, but minimally, and all the rest stays the same. Now, I mentioned before that there is this data space that was created as a binned space. You see here it's binned true. And we can also ask if it's binned and all of these things. But we can also do it more explicitly. We can say, okay, we have a space and we want to have that with the binning. So we can say the number of bins. Or we can just say, okay, I want to have some binning, and say, okay, a regular binning, number of bins minus 10 to 10, variable binning. And for anyone of you who's familiar with Boost histogram or HIST especially, this maybe already looks familiar, and that's because it is. The whole binned part in zfit should feel, as much as it can, UHI compatible, or a bit like HIST. It's also fully compatible with all of the definition of axis and everything. It's actually just a thin wrapper around it. So we can just create a space from a binning variable, and this can even be a hist axis, and we're getting something built. This one needs to run first, so that this also works. Exactly. And as said before, we can create data by calling it to binned and then give in this space. Before we just gave the number of bins, that gives a regular binning, but we can have any kind of like a variable binning, for example. So we can just create that, and you may also see this representation if it reminds you of hist. Again, that's because it is. Same goes for the model, which doesn't look so nice, but actually we can also plot it. We can just say to hist, and then we get our model as a histogram. You see, there's a lot of compatibility there. In fact, this is all compatible with UHI and libraries that do that. So we can say this .hist to hist, and we have hist. Again, we can sample from it, get it to hist, and anything. This we can do for the model. We can also do it for the bin data. But actually, the bin data is even easier because that is already this UHI compatible. That means it just behaves like a hist. And it has counts and values and variances. So it feels a bit like that. And you can also just say explicitly to hist, and you have actually your hist again. You can also use a hist object as input to zfit losses and fit that directly. So there's really nearly zero overhead to have this compatible. And now we go to binned PDF. This is our binned model. They're a bit different. They also have the same stuff as unbinned PDFs, but they work a bit different. And I think here's more CMS ATLA thinking in the way of we're having templates. We have these histograms. We're going to stack them. We think now in histograms. If we want to use binned PDFs for real, we can think of them just analytic PDFs that we make binned, but that's rather the small use case. We want to think we have binned models and want to vary these bins and so on. So they have two methods. That is, one is counts, which is counts that we expect, and we have the relative counts, which is the same, but just normalized to 1. Technically speaking, the counts in a histogram is the integral over the probability density function. So it's just, in this sense, the integral over PDF. You should be able to get all these bins, but it's a lot more efficiently implemented in this way. And the rest of it feels the same. You can, for example, say model.sample, and we're getting a bin sample, which is again this bin data object that behaves like a hist. And as mentioned before, it's UHI compatible. That means it has a lot of advantages. You can, for example, directly use npl-hep.histplot on this data object. That is just a binned data object that we created before. This is a zfit object. This is not a hist. And we can just plot our model by saying to hist. We can scale it up by the number of events. And yeah, we see exactly what is going on here. We can also, the bin sample is the one we just sampled before. We can also just plot this, where things obviously don't fully agree because it's randomly sampled. But we can also use just the PDF to plot it. We could also use this pdf.plot.plotpdf, the model.plot.plotpdf, but this is just more explicit. How we're doing things, it's all quite straightforward. We used before now a binned negative log likelihood, but we can also use other things. Extended binned negative log likelihood or a chi-square or something like that. So let's go and fit them. We can't just have a histogram PDF, which is like a trivial thing. It's like a histogram that acts as a binned histogram. We can create a yield though, and now we have a histogram PDF that is kind of scaled by this yield. We see here now, if we call histogram PDF.counts, there are 10,000 in here because this age scaled is a histogram that has 10,000 events. But if you explicitly say extended and say what's the signal yield, it gives us the exact number of that signal yield. So we have now a histogram-like model that depends on a parameter. The size, the strength of it depends on the parameters. And now we can have more things to do more advanced bin fits. If you're not so used to bin fits, then this is maybe a bit complicated at first sight. We can have some bin-wise scale modifiers, so scale each bin by certain parameters. We can create them explicitly and give them as a list, or we can just say true and it creates the parameters for us. Here's the way to create them manually. So all these modifiers, yeah, we have now 50 modifiers because we have 50 bins. And we have our yield, and the yield looks now a bit complicated because this is technically the sum of all of these modifiers and so on. The point here is you don't need to understand this, but this is all the stuff that zfit does behind the scene. All that you need to understand is to say, okay, I want to have this histogram as my model, and I want to have this binwise scale modifier there, and that's it. And you can forget about all of these rest that just behind the scene. There's also something called morphing, and for morphing, it means we can have different templates that we take from simulation, and we interpolate between those and say it can vary in the fit because we're not so sure about the exact template. We see again here how transparent this is between binned and unbinned. We can just create a data object as before, and the only difference here is, well, we create some exponential data. We use as an observable, we use now the binned observable. And that means that instead of a data, it's actually a binned data that is returned. Now, we can do this explicitly. We can first create a binned object, an unbinned object, and then say to binned as we've done before, or we can do it like this and give a binned observable, or we can also use this from NumPy constructor and give a binned observable. It all should lead to the very same result. And what we're doing down here is we just create these histogram PDFs and say, okay, at which value do we think, how many sigmas away from 0, 0 is our nominal, the green one, and how does our template change? And we have an uncertainty in this parameter. We can call this parameter alpha. It's just a nuisance parameter. And we can create our background PDF now, do some spline morphing using alpha, the background hists, and also say this is extended. We can, for example, plot it here. Get an idea what that means. If we change this value, it will plot differently. You can try it out. And then we create actually binned sum PDF, signal model plus background model. We just plot it by saying to hist, so we have a hist. We could also just do mpl hep.hist plot. And now what we want to do is we want to constrain these modifiers and say that they're not free to vary, they're just free to vary with the Gaussian uncertainty. And that just means we create a lot of these parameters. Well, we want to sample from it first and create some sample where we vary these. So we just say, okay, for each modifier, draw a random normal, and then sample from it. We just say the params to sample from is this one here, and vice versa. So this is also something new that we can just say the params, and then we get the values here. We can add them, and we get our sample data. Here we're going to add some constraints. So we're going to say, okay, this has to stay within these Gaussian uncertainties. It shouldn't just vary randomly. We create an extended bin negative of likelihood, and here the same game starts. We create minimizer. Well, we have to minimize it already. We minimize it, and then we can plot it. And as a notice, you also realize in general, when you run the fit the first time, it takes a bit longer. And that is because zfit compiled things behind the scenes. And that means that subsequent runs can be a lot faster, or if you're having larger amounts of data. This is all because it runs some TensorFlow and fancy stuff behind the scenes that is not so relevant, but you should know, okay, it does some compilation, and then it's a lot faster if you rerun things. Now we can also go back. We have our single PDF that is binned. We can use a spline PDF to interpolate. Now we get the unbinned spline, and again, we do just a simple plot. I mean, yeah, 2 lines. On one hand, we have the binned model, and on the other side, we have the spline model. And we can now use that. All right. This is, I think, all that is needed to understand the binned part and the unbinned part and how all these things go together. I think the real question is now, okay, can we see a real example? Because what we're doing is a bit more complicated than that. And what we're going to do, this is again unbinned fit, but again, similar with binned fits, you can just mix them and go from one to the other and so on. We can have constraints. We've seen that before. And this is going to be essential. How do we add more knowledge? Now, I won't go through the code in this example because it's just a bit more complicated, but basically we just create some signal of something called a rare mode and something, and the background that is rare. And the idea is we want to fit a certain model to data, the actual mode that we want to discover, and there's not so much data, but at the same time, we want to simultaneously fit to another mode, which is a lot more abundant and which shares some parameters. So this helps us to stabilize the fit on the rare mode. Now we just create some sample data and create our observable. What you see again here, we're having a label, and we just define that with LaTeX. That's very useful because it helps us back with plotting. It gives something nice. We can load that into zfit. It's again the same as before. We just have a few more data objects and so on. And what is probably to note here is that this is also quite a new feature. Instead of adding the data manually, we can just create these data objects in zfit, which behave like this pandas data frame. Now we can say, okay, .concat, and then it concatenates these two. So now we have the signal data and the background data that we've drawn above here. We specify a number of parameters, an exponential as a background, a Gaussian to fit, and we just quickly plot it to get an idea of what is there. You see, by the way, down here, the label looks now quite pretty because it takes the label that we specified. Now, we can add a constraint. That means some additional knowledge. Maybe we know that a value mu from PDT or something has to be around this and this value. So we can just add some constraint. And we can just compare it as well with something where we don't have a constraint. If you want to add this for a for our likelihood, we can say constraints equals constraints, but we don't need to do that. We can just create a likelihood without constraint and have our constraint separately. And if you have the constraint separately, we can just add these things. So this is, in a way, the more elegant way to do. But it all boils down to the very same thing. We can create some initial values and minimize it, and we can get our result out. And that's it. So this is now just fitting the small data sample by itself using this constraint. However, we can also do it simultaneously. And simultaneously, we now say, okay, we have a signal of 40,000, so that's significantly more. We do the same game again as before. We just draw some more data. There we go. Let's do that in succession. And we want to share some parameters. Now, sharing parameters or making them dependent of each other is quite easy in zfit. If you use the same object in both places, that means it's the same parameter. But we can also do more fancy things. We can have so-called dependent parameters. These are a bit like a function. They're called composed parameter because they're composed of one or more, technically of 0 or more parameters. For example, if you want to have a shift, so we know these parameters are the same. Well, they were maybe, let's say we have maybe two parameters that they're different, but we know they're shifted by the same value. For example, to correct for simulation and data discrepancies or something. Now, what we can do here is we can scale them. For example, we can say, okay, our width between simulation and data is kind of the same. So we have a free scaling parameter. And then we can create just a function that's, again, an arbitrary Python function. Basically, we can take these in like that and just create a composed parameter. This also has a name. It has a function. What parameters does it need? And we can say unpack params, which means we can take them like that. Alternatively, if we don't do that, it just gives us one thing, a dictionary that is params, and with all these parameters in there. Now we create our resonant model. That is also nothing fancy here. And we just create them now using this sigma scaled to fit. And if you want to now do a simultaneous fit, so we now want to fit the small PDF and the large one together, we can just do an extended unbinned negative likelihood of both of these, and then just add them. That's it. And we have a simultaneous fit ready. Now we can look at things, but we can just minimize that and then get the uncertainties. There we go, uncertainties, and we can just print our whole result actually. And this is it. If you want to plot it, that's quite trivial because we now have all the PDFs separately. So we can just go ahead and plot them. We'll just, for convenience, provide a function here. You can look at it, but it's kind of the same. Notice that it uses the small trick. We don't need to histogram things. We just tell zfit, make it binned, and we can plot it and make it a bit, let's say, nicer. And that's a plot. On the left, we see the small fit to the rare mode. On the right, we see the resonant mode. They were fit simultaneously. Now, the question is, of course, is this discovery? What's the significance of this? And we have our small uncertainties up here. but in general, we want to again use something more sophisticated, and that's where again hepstats comes in. Now, if you want to compute the significance of that, we can't just rely on this Hess approximation or minus, but we want to do something else. We take the parameter of interest from hepstats and say, okay, this is our signal yield. We want to say the null hypothesis is that we don't have a signal. And now we want to test this against if we're having signal. This here explains quite nicely what this all is about and what it will give out and what sigma means. But the technical thing is again the same. We have our zfit objects, we have the loss. This is now an analyze simultaneous, and we have our minimizers. We again get an asymptotic calculator, and we can already provide the best fit. We don't need to, it does it automatically. Otherwise, we can use the thing here and just use this time discovery instead of, as before, the confidence interval. Yeah, there we go. And this will calculate our significance, which would be 7 sigma. This is the p-value on the left, and on the right, it's the significant. We're above 5 sigma, so this is clearly a discovery. We can also do upper limit calculations, and the only difference here is if this will be done now with we can kind of play this game again and use a smaller sample. For example, if we just have 10 signal yields, we can create a loss that has a very small signal yield, so just 10, and see, okay, we can't measure it, but we can actually do an upper level of significance. This follows the same trend. We just create an extended log likelihood with just a small signal yield, and we can now use the upper limit clause in hepstats, compose things together. It's all, I think, quite self-explanatory, and with a nice utility, we can also plot it. For anyone who knows about splot, this is a way to disentangle signal and background. This is also directly available in hepstats. So if you have a zfit PDF and you fit it and you want to get the S weights for it, it's quite simple. This just does a standalone example of it. And yeah, we can then fit it below and just get the S weights out. The whole step that we need to do is we have our model, we have our data, that's all from zfit, and we say compute S weights, and we're getting the S weights out. There we go. We're just doing this small example. This is a mass fit, and this is the variable we want to disentangle. If you're familiar with S weights, we fit it. This is fit. And we're getting the S weights out. And what that means is if you're plotting things now using this variable, this is what it actually looks like now. So blue is now using these weights. But yeah, be careful with it. And last but not least, I'll tell quickly about custom models. That is the probably most significant part in zfit, which means you can just create your own PDF shape. And that means, again, we start out just importing things, and now we can overwrite what we actually want. So if you want to create a second-order polynomial, for example, we can just simply, well, use the snippet and overwrite _PDF. There is also the way to overwrite the unnormalized PDF, but the more modern way is actually to do this thing. We're getting in the parameters, and we do whatever we want. Now, that's all that is needed to create your own model in zfit with 2 parameters. In fact, we can just create here a model like we did before, a PDF, and we have all the same methods available as for any other model. So we can integrate, we can sample from it, we can get the probability out, whatever, we can fit it. That's all that is needed. There are things numerically if you don't provide them, but you can always add things. For example, you could add an integral. You can add a CDF, you can write your integral function and just register it. We won't go through it, but that means just now we have an analytic integral, and we see we have here something print integral called, and we see now here the integral is getting called when we're doing these things. Scikit really uses this function now and makes it a lot faster. We can also go multidimensional. This is a quite complete example, and it's just to show you what you can actually do. You can go to your paper, take an expression that you have for some angles, for example, implement things. Yeah, looks a bit more complicated. All that you need to remember whenever you implement something here is to just use the ZNP. Yeah, okay, you can just do multiplications, or otherwise you can use this library, ZNP here. ZNP is like NumPy, but it actually uses TensorFlow behind the scenes, and this means that things get a heavy speed up. But it's the same. We can have multidimensional spaces. We can just create a one-dimensional space here and here and here. We can multiply them. We have a three-dimensional space. And we'll just manage these with dictionaries and stuff. We create a Wrangler PDF. That's all and straightforward. We can multiply it and so on, but that's not so crucial. If you are interested in what really happens behind the scenes, you can look at that, but that's not so relevant. We can also, what we didn't do, we can also say we want to normalize it manually, for example, and say the norm here is true. So we build again our model, and we just say norm equals true. There's all the power with the user. You can hack your way through. If you don't hack your way, zfit has in general you covered. We can do the same for binned PDFs. As we've seen before, they have the counts and the relative counts. We can, for example, just make a mixture of two histograms. Say, give me histogram 1, histogram 2, and the fraction parameter. We store the histograms. We say, okay, the parameters, we call them frac, and say frac. And here we just have these other arguments, which we in general don't need to care about. We can just leave them. We can be smart about them, but we can also just give them to a superclass. And then we define here the relative counts. So we say, okay, the superclass takes care of the whole yield and stuff. And we just get our parameter out. We create the sum of these two, the counts of the histograms, and that's it. As before, we can create some data, hist1, hist2, get a fraction parameter. We can create our mixture, and now we can get the relative counts. We can plot it. We have now the mixture of the two parameters. And we can also just create a sample from it, for example. We can also use a different fraction. We call fracbin. This is the parameter name. So frac here is called fracbind. So we say use fracbind to be 0.3. And we can plot it 1 peak a bit higher. There are also more advanced things, like we can make composed PDFs. And that's basically the same thing. We just need a different inheritance. And we need to provide the PDFs that it depends on. So it handles all the dependencies correctly. But this is more for you to explore if you're interested in some more advanced concepts. We can, in principle, also mix in some pure Python into it. But this all is for you to read up if you're really interested. All right. With that, we're concluding this talk, this walk through zfit, and I would like to open the room for questions.
Okay, thanks very much. I think we have at least 5 minutes or so for questions, so if people can please raise their hand. Okay, I think I saw Alexander's hand go up first, so we'll go to them.
Yes, hi Jonas. Thanks a lot for the nice presentation. I've been using zfit quite a lot, and what I noticed that when you also see in your notebooks, that you very often do the same things over and over, right? You define a parameter, the different models, then the likelihoods when you minimize. I was wondering if you plan to maybe provide an API that automatizes some of the steps in a way that the user could provide a config file, like a YAML file that defines, for example, just in plain text the model and the parameters, and then it can give to zfit and execute the fit without writing all the repeating steps very, very often.
Yeah, thanks. That's a good comment. And I think it's both a yes and a no. So on one hand, maybe for the yes part, yes, in the way that this is in general the idea, the way we're building zfit is we go with the core building blocks and make sure that they're always the same, because sometimes it's I think easier to have consistency, and writing 3-4 lines of code more usually doesn't harm at all. If you're writing your own analysis, that's 10,000 lines of code, but it's explicit and it all works. And then we start from over time, and we're now at this point basically to provide these higher level interfaces. I think a nice example of a recent, I mean, Yasin will later on actually talk about these few shortcuts, but like plot PDF and things like that. And one of the things there is also to have a better interface to do stuff, to do common fits. The problem there is a bit, what are common fits? Let me divide that. Since you asked about the config file, yes, there is already a way. If you use this like the YAML format, then that zfit dumps to, then you can basically just load this as well, and you get your PDF back, or you could even technically have your, well, NLL, but that contains binary data, so it's probably a bit harder. And so the question is there a bit, there's such a huge thing. What exactly would you expect? If you have something good in mind, then we can probably offline discuss it. But I think in general, for a general thing, it's very hard to say, okay, just this config to do that. But there are specific use cases. And I think binned fits, for example, these like histfactory, PyHF style, for example, that reoccur a lot, but makes a lot of sense to have some interface to add something more easily. And we're basically in the way of adding these things now. So if you have some specific ideas or wishes, yeah, offline discussion would be great, but we're also doing that up to a certain point. Not to everything, because in the end, I think there are just so many ways that people want to do fits, and they're so different, and that would simply overload. But specific things are very welcome, and we try to add them more and more to make shortcuts, to make it easier, to make things, as you will see also in Yasin's talk later on.
Yeah, thanks a lot.
Yeah. And if memory is correct, there's zfit also has quite like an extensive GitHub system for issues and discussions. So I believe that's the place you want people to raise things, correct?
Yes, exactly. Yes, thanks.
Okay.
Thanks. That's true. There's actually, yeah, you can also go there and ask, and yeah, we have some discussions there too.
Great. Okay, so Yasin, well, let's go to you.
Yeah, hi. I just had like just one curiosity because I'm not familiar with hepstats a lot. Does the asymptotic formula calculator, does it implement like all the statistical tests from the old paper by Glenn Cowan, Kyle Cranmer, and so on for that we used for the Higgs discovery?
I would say no. If you ask all the tests for the Higgs discovery, no. I don't well, I think it just implements a few things.
There's like four statistics and their distributions, I think, if I remember correctly, implemented in that paper. And it's like discovery, upper limit, and yeah, and so on.
Yeah, I think there's discovery, there's upper limit, there's a confidence interval. Yeah, I think actually, yeah, that's true. I think the relevant things are there. Yeah, I'm not sure what exactly was implemented in. So I'm not familiar with the Higgs analysis in a technical sense. But yeah, I mean, that's also very open to extension. It's quite modular, so this could be added if something would be needed there.
Yeah, I'm talking about the paper that I just pasted in the chat. Like,
oh, sorry, I didn't see.
Yeah, no, I just pasted. Yeah, it's basically like it provides a asymptotic formula for some test statistics, and they calculated the distribution of those test statistics for.
Yeah, I think these are actually the one that are there. These are actually, I think, the one that are there. But I'll have a look at the paper to make sure.